In this video, we're going to look at density and specific gravity. In this video, we're going to talk about what density is, the definition of it. Then we'll talk a little bit about how we can decide if something will sink or float, and we'll compare some common densities. And then we'll look at calculations that involve density. And finally, we'll talk a little bit about specific gravity, which is very closely related to density. So let's start with the definition of density. Density is defined as the ratio of the mass of a substance to its volume. This is often written as D equals m over V. The normal units that we use are grams per milliliter, that's in the metric system. In the American system, they may use pounds per cubic foot, but we will not be using the American system at all in this course. Some other units that you'll see for the metric system, sometimes you'll see grams per liter, although that is rare. The other ones that you commonly see, though, are grams per cubic centimeter or grams per cc. And so those two are both commonly used because they are exactly the same as the grams per milliliter unit. Recall that 1 cc equals 1 cubic centimeter equals 1 milliliter. This relationship is similar to the way that we think of population density. So you might say that in an urban area, like in the city, we have a high density of people. There's a lot of people in the volume of that city. Normally we think of it as an area, but recall that in big cities like LA and New York, they have tall buildings. So we're looking at how many people we can pack into the volume of those areas, and there's a lot of people, so it has a high density. That would be like a high mass to volume ratio. On the other hand, if you live out in the farm, there's one person per acre, maybe, and if you're out in that area, we're going to have a very low density where there's very few people given the same volume. And now we're going to answer an age-old question. Which one weighs more, a ton of feathers or a ton of bricks? So think about it for just a moment. So let's look at the question carefully. And we see that we have which one weighs more, a ton of feathers or a ton of bricks. Notice that they are both in the same measurement unit, which is ton. That is a weight in the American system, and so they are the same. A better question might be, which is bigger, a ton of feathers or a ton of bricks? And think about that for a moment. Pausing your video. Hopefully you guessed that the ton of feathers is larger than the ton of bricks. But why is that? They weigh the same, but we know that the feathers are far less dense than the bricks. The bricks are very, very dense. So when you have a higher density, things are compacted more. More things are packed into the same volume. And now I have a simpler question for you. Which one weighs more, one brick or two bricks? Well, this one should have been a lot easier for you. Assuming that the bricks are the same size and shape and style and made of the same chemicals, then we would find that the one with two bricks should be more massive, way more, than the one brick. In fact, the amount should be twice as much. So that means if one brick is 5 pounds, two bricks should be 10 pounds. Or if one brick is 2.27 kilograms, then two bricks should be 4.54 kilograms. And this is what it would look like if we drew it out. For the one brick, we would draw a box and put 5 dots in it for our 5 pounds. And in the second one, we're going to draw 2 boxes, each with 5 dots in them. And here you can see that we've doubled the mass because we've doubled the volume, and the density was the same. Let's see if we can figure out the density of one brick. For one brick, if the dimensions of the brick are 20 centimeters by 10 centimeters by 6 centimeters, we end up with 1,200 cubic centimeters as the volume of our brick. If the mass of one brick is 2.27 kilograms, then we would know that that is 2,270 grams. Now we're going to calculate the density. The density is the mass divided by the volume. The mass in this case was 2,270 grams. The volume was 1,200 cubic centimeters. When you take 2,270 and divide it by 1,200, you'll get the answer of 1.89. Now the units are still going to be grams on top, cubic centimeters on the bottom. And that would be the same as grams over milliliters, but we found it as grams over cubic centimeters. What if we try to find the density of the two bricks? Well, again, we're going to start by first finding the volume of the bricks. In this case, again, each brick is 20 centimeters by 10 centimeters by 6 centimeters. So each brick is 1,200 centimeters cubed. Put them together. We're going to add those two together for the total volume of 2,400 cubic centimeters. The mass is now 4,540 grams. And so we'll take 4,540 grams, divide that by 2,400 cubic centimeters, and we end up with the same answer of 1.89 grams per cubic centimeter. And again, this is not surprising because we have the same chemical, we have the same substance, the density should be the same. These are some theoretical densities of a variety of different materials. Theoretical means that that's what we expect it to be. It doesn't mean that experimentally we found that number in our experiment. We might find it on average. Most people will get this answer, so we call that a theoretical density. Now, theoretical densities do depend upon temperature and some other things, so I don't expect you to memorize these or know them, except for one. I'm going to have you remember that water, liquid water, has a theoretical density of 1.0 gram per milliliter. You do not have to do anything with the American ones. We will talk about it a little bit later, but for the most part, we're going to ignore the American units. I'm asking you to recognize the theoretical density of liquid water because we use it a lot throughout the semester. It's not like it's a magic number, but we do use it throughout the semester, so if you know it, it will make everything easier for you as we go through the course. So what can we do with these densities? Well, probably the major thing that we do with density is to look at whether something will float or sink. Now, normally we're going to be looking at water, so we're going to use that density of water of 1.0, and we're going to compare to that density. We could also do other liquids, in which case we would compare whatever substance we're looking at to that liquid to decide whether it floats or sinks. So notice that this list, starting from oak and going down, is going from the least dense to the most dense. Notice that oak is less dense than water, and that is the only one that was able to float on water. And you've probably seen this where a piece of wood will float on top of water. Oak is the only example we have, but there are lots of other ones that would have those lower densities. Now we look at aluminum, cement, lead, and gold. Those all have densities that are greater than the 1.0 that we find for water, so all of those will sink in water. If you find something that has a density very close to 1, you'll see that that substance will float sort of in the middle. It won't sink all the way to the bottom, but it won't be floating way up at the top either. Whether something sinks or floats is actually related to its buoyancy. Buoyancy is very closely related to density, but they are not exactly the same. To determine whether something sinks or floats, we discuss its buoyancy. When we talk about how much material or matter is packed into a volume, we're talking about the density. They are not the same, but they are very closely related. As I mentioned, we can use density to decide whether something will sink or float. And whether something sinks or floats is known as buoyancy. So density and buoyancy are very, very closely related, but they are not the same. So this will not be on the exam. I just wanted to explain a few things because sometimes people get confused about it, and that way you can see how density and buoyancy relate to your life. Let's start with the definition. Density is defined as the amount of mass in a given volume. It talks about how many particles are given inside of something. Buoyancy is defined as whether something floats or sinks in another substance. Buoyancy doesn't specify how much matter is present in a given volume, but it does use density to determine whether something is buoyant or not. And now I have a puzzling question for you. Why does the Titanic float? Why is this a puzzle? When you think about the Titanic, you know that the majority of it is made out of steel. That steel has a density of about 8.5 grams per milliliter. We're floating in water. In this case, it's salt water, so it's a little bit higher than 1, but we're going to say it's about 1, and we know that the density of water is 1.0 gram per milliliter. We see that the density of the steel, 8.5, is much greater than the density of water, and we would expect that the Titanic should sink. Why doesn't it? Here we can see that even though steel has a high density, the Titanic is buoyant. It is able to float on top of water. What we see is that when a ship is built, it is built with a very large, what we call cargo hold, but an area that has a lot of air in it. The combination of the steel and the air together is much less than 1.0 gram per milliliter, so that the density overall is less than 1, and now the ship will float. And now the second half of the puzzle. So why did the Titanic sink? Of course, everybody knows because it hit an iceberg and it sank because of that. But why did hitting an iceberg make the Titanic sink? Okay, you might say, well, of course, it filled with water. So what does that have to do with density and buoyancy? Well, at this point, as the cargo hold filled with water rather than air, the average density got closer and closer to the 8.5 grams per milliliter that you see for the steel, because the water was more neutral. It's the same as the water inside and outside stayed the same, so that the overall density became larger and larger until the boat sank. And of course, with the Titanic at the bottom of the ocean, we would say that it is not buoyant. This is a little bit of a simplification of how buoyancy works, but it does give you the basic idea that it depends both upon the density and the volume, and in this case the density of the average, including all of the air or water or furniture or cargo, makes a difference to the density of the ship and tells us whether it will float or sink. Too much cargo in a ship will also cause it to sink. When you actually look at buoyancy, you have to look at the amount of water displaced, and that is related to the volume of the ship. But we're going to keep it simple here. I just wanted to give you an idea of how it works. And recall, please, that this is not on the exam. Now, let's look at some calculations that you will see on the exam. In this class, when we do density calculations, there are essentially 3 types. The first one is to find the density. The second one is to find the mass of a substance. And finally, we can find the volume of a substance. When we do these, we are always given the other 2 pieces of information. So when we're looking for the density, we'll be given the mass and the volume. When we're finding the mass, we'll be given the volume and the density, and when we're finding the volume, we'll be given the mass and the density of the substance. As I solve each of these problems, I will show you 2 different methods that are commonly used. One method will be an algebraic method, which some people are very comfortable with, and the second method will be the one that I prefer, which is using dimensional analysis, as we've seen earlier in this class. This is the first of the 3 major density calculations. There are 3 different types because we're going to be looking for 3 different things: the density, the mass, or the volume. In this case, we're going to be looking for the density, and we'll be given the mass and the volume. To start these calculations, we need to recall that the density is the amount of matter that is given in a certain volume of substance. So when these questions, we're looking for what is the mass and what is the volume. So reading through the question, we have 25 milliliters of rubbing alcohol, which weighs 19.6 grams. We want to know what is the experimental density of the rubbing alcohol. The first thing we're going to do is identify the mass. So which of these numbers is the mass? You should see that it is 19.6 grams. Then we're going to find out what is the volume, and in this case the volume is 25 milliliters. And we're going to know our equation, the density equals mass divided by volume. So we'll take 19.6 grams and divide that by 25 milliliters. We put that in our calculator and we get the answer of 0.784, and the units will be grams over milliliters. In this case, it doesn't matter whether I'm using the algebraic method or the unit analysis method. They will both tell us the same answer, and the calculation will look the same. Here the difference is that we'll be looking for the units that we want for our answer. In this case, we know that we want our answer to be grams over milliliters. So we'll put whatever unit has grams, in this case the 19.6 grams, on top, and we'll put 25 milliliters on the bottom so that the units match up. Then we just plug that into our calculator, we get 0.784, and then our units will be grams on top, milliliters on the bottom, and we're done. And this is the second type of density calculation. In this case, we'll be looking for the mass, and we will be given both the volume and the density of the substance. This question says, what is the mass in grams of 50 cc's of cement? So we're going to do the algebraic method. We're going to need to rearrange our equation. We know that D equals m over V, where m is mass, V is volume, and D is density. To find just the mass by itself, we're going to multiply both sides by volume, and we'll see that the density times the volume is equal to the mass. So we can now solve for that by plugging in the numbers. Let's look at the numbers that we have. We have 50 cc's of cement. Is that density or volume? That's right, it's a volume. And so now we're going to look for the density. We'll notice that it's not given. In this case, it should be found in a table. Normally you'll find it in a table or it'll be given in the question. So let me show you where it is on the table. And from this chart, we can see that the density of cement is 3 grams per milliliter. Following the algebraic expression, if the density is 3 grams per milliliter, we'll plug that in, we'll put 50 cc's in, and we'll see that our answer is 150. That's the numerical answer. Now if we look at the units, it is 150 grams per milliliter times cc. We know that cc and milliliter are the same, so they end up canceling out. And we have the answer of 150 grams. Now let's try the unit analysis method. In this case, we have the same information. We know that we have 50 cc's as our volume of cement, and we know that our density is 3 grams per milliliter. So now let's see where we start. We have two places to start. We could either start with the 50 cc's, the volume, or we could start with the density, which is 3 grams per milliliter. Now notice that the density has grams on top, milliliters on the bottom. We prefer not to start with that as our equation. It's generally preferable to start with one that is not a ratio. So in this case, I would start with the 50 cc's of cement. Now our ratio doesn't go to cc's. So we're going to do another step, and we're going to either cancel this out right away and write it as 50 milliliters of cement, or we could just go ahead and do it as a multiple step unit analysis and say 50 cc's, and then what goes on the bottom will be cc, and we have 1 cc equals 1 milliliter. So now the cc's are canceled and we're left with milliliters. We can see how that relates to the density, because the density is 3 grams per milliliter. We're going to put milliliters on the bottom to make sure the milliliters cancel out, leave the grams on top, the 3 stays with the grams, and we get our answer of 50, all those units are canceling out, times 3 grams, and that is equal to 150 grams. Of course, the answer is exactly the same because it's the same question, but there are two different ways to get there. And this is the third type of density calculation. In this case, we'll be looking for the volume, and we'll be given both the mass and the density of the substance. Let's start by reading the question. We see that it's asking, what is the volume in milliliters of 32 grams of gold? And again, we're given this table to tell us what the density of gold is. So we look for the density of gold. We see that the answer is 19.3 grams per milliliter. Of the 3 types of density calculations, this one is the hardest to solve algebraically. So we'll go ahead and set up our equation that we know. Density equals mass over volume. We're looking for volume in this case, so we're going to actually have to multiply both sides by volume. So we have volume times density equals mass, and now we have to divide both sides by the density, so we have that volume is equal to the mass divided by the density. We'll go ahead and put those in. Now we're going to put our numbers in. So we see that volume is equal to the mass, which we have 32 grams, divided by the density, which is 19.3 grams per milliliter. And that leaves us with our answer, 1.658, and those units will be grams over milliliter. And obviously that is not what we're looking for. We're looking for just milliliters on the top. If we focus on just the units, we can see that we have a fraction that is divided by a fraction. The upper fraction will be our grams, and that's going to be divided by 1. And the lower fraction is going to be our grams over milliliters. Now, you may or may not recall, but when you do this, you're going to do, when you divide a fraction by a fraction, that means you take the bottom line and you flip it upside down. And now we can see that we have grams divided by grams, and they cancel, and the milliliters is on top and the 1 goes on the bottom, which means that we do have the unit of milliliters. Much harder to find that unit of milliliters this way though. Now let's try the unit analysis method. In this method, we still have the same two pieces of information. We know that we have 32 grams of gold, that's our mass, and we know that we have a density of 19.3 grams per milliliter for gold. So where are we going to start this problem? When we're doing unit analysis, again, you have a choice of where to start. Always start with the one that is not a ratio. Notice the 19.3 grams per milliliter is a ratio of grams to milliliters. So the best place to start this problem is with our 32 grams of gold. You start with your 32 grams of gold, then you're going to put grams on the bottom in the next part of the question. Notice that we have grams on the bottom, and that means we're going to change it to milliliters, so grams on the bottom, milliliters on the top. The 19.3 stays with the grams, and we put a 1 with the milliliter as a placeholder 1. And now we do our solving of the equation, and we get the same answer of 1.658. And in this case, it's much easier to see that the units here is milliliters, as we expected. I'm providing 2 more types of calculations for density. These will not be on the exam, but they are certainly going to be found on your lab, in your lab, and on your lab quizzes. So the 2 ways that we can do this is to look at the density of a liquid and the density of a solid. And in these 2 problems, we have to do an additional step to find the mass or the volume. And we'll see that on the next 2 problems. While there are only 3 major types of calculations with finding the density, where we use the mass or the volume, or finding the mass or finding the volume, we do know that sometimes we have to do extra steps to find out what is that mass or what is that volume. And those steps can be done in a laboratory. So here we're going to give an example of finding the density of a liquid where I don't tell you the actual amounts to start with. You'll have to measure those. And so this is an example of how you would do it in a lab to find the density. When trying to find the density of a liquid in a lab, one of the big challenges is finding the mass of that liquid. If we just pour the liquid right on the balance, we'd make a huge mess. Obviously, we don't want that to happen, so we pour it into a beaker or some other container. If we pour the liquid into the container and put that onto the balance, we now will have the mass of the liquid plus the container, and that won't work. We want just the mass of the liquid. So what we do instead is we first weigh the empty graduated cylinder, find out its mass, then we're going to add the liquid into the graduated cylinder, and then after that we'll find out the mass of the graduated cylinder plus the liquid. Then you just subtract out the mass of the graduated cylinder from the mass of the graduated cylinder plus the liquid, and we find out the mass of just the liquid. And now you just do a regular density calculation. Let's use our sample data. First, we'll look at the mass of the empty graduated cylinder. Here we see that it is 94.13 grams. Next, we'll measure the volume of the liquid that was added to the graduated cylinder, and we can see here that it is 24.0 milliliters. And finally, we'll weigh the filled graduated cylinder, and in this case we see that it is 117.39 grams. Now, let's find the mass of that liquid. By subtracting the empty cylinder from the filled cylinder, we will find just the mass of the liquid. The mass of our filled cylinder was 117.35 grams. We're going to subtract out the empty cylinder, which was 94.13 grams. And we find our answer to be 23.22 grams. So now we have the mass of the liquid and the volume of the liquid. We just need to do the calculation. Since we're finding the density, we'll put the mass on top. That's our 23.22 grams. And then we're going to divide that by our volume, which is 24 milliliters. And we find our answer to be 0.9675 grams per milliliter. Next, we'll look at how we can find the density of an irregularly shaped solid, one that we can't just measure to find its volume. Up to this point, we were able to find the volume of a substance by either measuring it, if it was a solid, by figuring out the length, the width, the height, and figuring out the volume. Or if it was a liquid, we would just measure it in a graduated cylinder. But what happens if we have something that has an irregular shape, something that's really hard to just measure the length, the width, and the height? For that type of thing, we have another method to discover the volume of the solid. As usual, to find the density, we will need both the mass and the volume. We'll find the mass first, and that's just by putting the solid onto a balance and weighing it. And now for the challenge, to find the volume of this oddly shaped solid. So for this, we're going to fill a graduated cylinder with some water. You need to add enough liquid to cover the solid. And then we're going to find out that volume of liquid water that we have in the container. We're going to add the unusually shaped solid into that cylinder and find out the new volume. And by subtraction, we'll find out the volume of the solid. And finally, we'll calculate the density by using the measured mass of the solid and the calculated volume of the solid. Let's see what the result is of our experimental calculation. We'll be filling out our data table with this information. We're going to find the mass of the solid. Reading from the balance, we see that that is 482.63 grams. Then we're going to read the volume of just the liquid in the graduated cylinder, and that is 600 milliliters. And we'll find the volume of the solid and the liquid in the graduated cylinder, and we can see that that is 800 milliliters. Now we'll make a calculation table. We'll be subtracting the volume of the liquid from the volume of the liquid plus the solid to find just the volume of the solid. So we will have 800 milliliters minus 600 milliliters, which leaves us a solid with a volume of 200 milliliters. And finally, to calculate our density, we'll take our mass, which was 482.63 grams, and we'll divide it by the volume of the solid, which was 200 milliliters. And that gives us an answer of 2.41315 grams per milliliter. And our last topic will be about specific gravity. Specific gravity is strongly related to density. They are not the same thing, but they will seem to be the same. I'll explain as we go on. The specific gravity of a substance is the ratio of the density of that substance to the density of water. For example, let's try to find the specific gravity of gold. On the previous page, we saw that the density of gold was 19.3 grams per milliliter. We're going to be using that in this equation. Recall that the density of water that you were to memorize was 1.0 gram per milliliter. Therefore, the specific gravity of gold is equal to 19.3 grams per milliliter divided by 1.0 gram per milliliter. We calculate that, we get the answer of 19.3. Now what units are left? It ends up that the grams and the milliliters all cancel out so that we only have 19.3 with no units. And that's what's very different about the specific gravity. The specific gravity of gold in both the American units and in the metric system is 19.3. So how do we use this in a problem? Well, there's a couple of ways we can use it. First, if I asked you, what is the density of cement if the specific gravity is 3.0? Your answer would be the density is 3.0 grams per milliliter. Well, that's a pretty basic question. Let's make this one step harder. So what if I said, what is the mass of 20 milliliters of sulfuric acid if sulfuric acid has a specific gravity of 1.5? All you would do is you would start with your 20 milliliters of sulfuric acid, multiply that by 1.5, add in the grams over milliliters because specific gravity and density are the same except that density has those units, and you'll get the answer of 30 grams. I don't usually put specific gravity calculations on my exam, but you should know the definition.